All right, welcome back and happy Wednesday to you all. I made a mistake in the last lecture that Jasper pointed out very kindly, and I'm embarrassed. It didn't turn out to be a huge deal, but I just want to acknowledge it here. In the recorded video, I edited out the wrong portion. Should any of you go back and watch that so you won't be misled. The place where I made a mistake is where we were talking about better orbital overlap leading to greater stabilization. And the mistake I made was, I don't know if you remember back in the two orbital mixing problem, we actually solved for what the energies of the bonding versus anti-bonding orbitals were. I told you something yesterday that or on Monday that made sense to me, but actually isn't true. So the energy of the bonding orbital is the core integral plus the resonance integral divided by 1 plus s, not 1 minus s. S is the overlap integral. And if you look at it this way, better overlap should mean a larger S, and so that would lead to less stabilization, right? A less low in energy orbital. What the heck's going on there? And I think I mentioned that we've dealt with this rather simplistically, assuming that we could change these parameters independent of each other. The resonance integral and the overlap integral are related to each other. So you can't just arbitrarily increase the overlap integral without also making this energy more favorable. So I don't have a mathematical justification for you why better orbital overlap leads to greater stabilization, but that is a principle we will use. And I'm sorry I got confused. If you want to just forget my explanation for that and remember the principle, you should be just fine. So I apologize for that. All right. We were beginning our qualitative molecular orbital theory approach for CH3. And here we're doing what the physicists do when they assume a spherical cow. We are assuming a trigonal planar CH3 without even worrying about how many electrons or really whether it's even trigonal planar. So we defined our coordinate system. We decided our first and lowest energy combination would be with the 2s orbital on carbon combining with 1s orbitals on each of the hydrogens. We called this a sigma type bonding orbital because most of the electron density is in the space between the nuclei. Now this doesn't correspond to any particular sigma bond. Remember, this orbital would hold 2 electrons and they'd be delocalized across the whole molecule. Nevertheless, they would tend to spend their time in between the 2 nuclei. That's a sigma type arrangement, and it's a bonding type arrangement. We talked how another option would be simply to combine the 2s and the 1s atomic orbitals with opposite wave function sign. And you get this orbital. And your text calls this weakly antibonding, by which I think your text means that s orbitals don't actually overlap with each other that well. They're projected spherically similarly in all directions, and so the out-of-phase interaction there is not that destabilizing. All right. So our next option was to combine one of the p orbitals, in this case the 2px, with the 1s orbitals from hydrogen. And based on our coordinate system, x is just the x-axis is just up and down. So 2px happens to coincide with the bond between carbon and this hydrogen up here. So you would overlap this lobe of the p orbital with this 1s atomic orbital on hydrogen. And then on the other side, where wave function sign switches, you would have this orbital, this lobe of the orbital sort of overlapping with these hydrogens. This is sort of difficult to see from the side. So if we want, we can imagine what this would look like from the top. If we now are looking down the z-axis, we would see an orbital kind of like this. Oops, I like to use gray for orbitals. And then another orbital like that. Or if you wanted to draw it out schematically like we've done before, where you can see each of the individual atomic orbitals that we mixed together to make this molecular orbital, we would have the p orbital here, okay, so two different views. You see where that comes from? In this case, we're not concerned that the orbitals don't sort of overlap directly end on end. We don't care that they're not pointing in directions that correspond to the bond. It's okay that this lobe of the p orbital is projecting out into the space between two bonds. And here's the interesting thing that I realized when I was first teaching this class. You mix together s orbitals, what you get out is something that, if you squint, looks sort of like an s orbital. It's just one lobe of electron density. You mix together something involving a p orbital, and you're going to get out a molecular orbital that looks like a p orbital. It's a little bit different because it encompasses more atoms, but can you see the familiar pattern there that looks kind of like you would draw a p orbital? Yeah.
Can you just move that little box?
I am so sorry. Gosh, thanks for one of these days I'm going to remember and not need the reminder. There we go. So we draw just a regular p orbital, it would look something like that, and the comparison is actually pretty good. All right, other questions about that? There'd be an out-of-phase combination as well that we won't worry about too much. The next option was to mix the 2py orbital with some of the s orbitals. So the 2py orbital should be aligned along the y-axis, sort of coming out at you, out of the page, and then going back into the page. And this is difficult to draw, so we're sort of taking a side-on view. Notice that the 2py orbital has a node in the xz plane. That is, electron density goes to 0 as you go from this lobe to that lobe, and that node where electron density goes to 0 is the plane that's sort of marked out by these x and z axes. So what that means is, the way we've oriented our molecule, this carbon-hydrogen bond is in the xz plane, aligned along the x-axis. So that hydrogen actually is in a node, and there can be no electron density at it. Wave function equals 0 on that hydrogen. All right? But we can overlap the hydrogen that's pointing out at us with the lobe of the 2py orbital that's pointing out at us with an in-phase interaction. And then we can do the same on the other side, just with the other wave function sign. And naturally, if you wanted to, you could draw the out-of-phase combination where everything would really be in the same place, only there would be a switch in the phases. So blue lobe in the front, yellow lobe in the back, yellow lobe here in the front, blue lobe in the back. So this is the kind of orbital that would have two nodes. There would be one here and another corresponding to the xz plane. All right. And then, let's see, is that it? Go ahead.
So with the 2py, where? Oh, sorry.
That's fine. Okay. Now, if you're keeping track of sort of what we've used so far, of the available orbitals that we began with, on carbon we had a 2s, a 2px, a 2py, and a 2pz. And on hydrogen we had 1s orbitals. Um, we've used pretty much everything except the 2pz orbital. So let's draw what it looks like when we try to make a molecular orbital out of that 2pz orbital using trigonal planar methane. So remember our coordinate system x, z, and y. The 2pz orbital is going to be oriented along the z-axis. And notice that it just so happens that the node of the 2pz orbital is the xy plane, and all the hydrogens and carbon are in the xy plane. So there can be no wave function equals 0 in the xy plane. There can be no orbital density on either the hydrogens or the carbon in that case. All right. Let's just pause to verify that what we've come up with obeys the symmetry requirement. Remember, these orbitals have to be symmetric relative or antisymmetric relative to the symmetry properties of the molecule. So the first one's kind of a no-brainer. You rotate around the z-axis by 120 degrees and you get the same thing. Same here. The symmetry element that we are symmetric with respect to is this axis, which is a C2 axis. 180 degrees, rotate that, and we exchange the position of the hydrogen in the front with the hydrogen in the back, and we see exactly the same wave function sign. This orbital out here, the out of phase combination, obeys that as well. How about the 2py orbital? What if we do the C2 symmetry, the C2 axis of symmetry, we take the hydrogen in the front and rotate it to the back? Does that still keep the rule? Yeah, it does. It's antisymmetric. The wave function sign changes. So we're keeping that rule. We could say the same over here. And then we keep the symmetric rule here about the C3 axis. We also keep the anti-symmetric rule here about the C2 axis for the 2pz orbital. Okay, so it's good to check and make sure you're keeping the symmetry rules. Now, let's think about how we might order these in energy. And the principles we're going to use to order these in energy are: first, orbitals with s character are lower in energy with orbitals that are mostly p character. Bonding orbitals with in-phase interactions are lower in energy than anti-bonding orbitals with out-of-phase interactions. Another way of saying that is more nodes generally means higher energy orbital. So if I had to pick among my options, which is going to be the lowest energy one? Probably the first one we did, right? We can call that A for lack of, just because, I don't know. And next might be, okay, what do you think about next? What would be our next set of orbitals? Again, look for bonding versus anti-bonding interactions. Okay, good. 2px, why would you say that?
Well, it only has one node.
Just one node here, right? If we could draw the nodes. I'm not sure what we want to use for the node. Maybe orange. We've got a node there. And then we've got a bonding interaction there and bonding interactions there. Okay? So let's, I agree, and we'll call that energy level B. How about this next orbital? What would you call that? Or rather, would you call that a bonding orbital? Are there places where two parts of the orbital are side by side in phase? Sure. Right here is a bonding interaction. Right there is a bonding interaction. And there is one node. The node happens to be the plane of the page. I guess one thing I neglected to do when we were talking about this orbital that comes from the 2py is to draw what it would actually look like. And if you were to draw this orbital, you would see a lobe that sort of hovers above the carbon and encompasses that hydrogen, and another lobe that hovers below the carbon and encompasses the hydrogen in the back. And if we viewed this from the side, what it would look like would be this. Okay. So in terms of nodes, which one of these, B or I guess we'll call this C, which one of those should be higher in energy? Or do you think, what do you predict their relative energies to be?
I feel like C would be higher in energy because B has more s orbitals in it.
Okay, you feel like C might be higher in energy because B has more s orbitals in it. I think that's a reasonable hypothesis because you do have a node encompassing one of the atoms. Though it turns out that if you think about the type of bonding interaction you've got here, you've got a direct lobe pointing towards this hydrogen here. You've got a more indirect interaction here. So we've got one direct interaction and two sort of indirect interactions. And we're replacing that with a slightly less indirect interaction here and a slightly less indirect interaction there. If you look at these orbitals the way they appear from the side, it just looks like this is a p orbital and this is another p orbital. And so it turns out they're the same energy. So when we have two unique orbitals that are the same energy, a mathematical word for that is degenerate, or just same energy. And then finally, we would include, aside from the antibonding orbitals that are available, we would include the 2pz orbital, which should be higher than any of the bonding orbitals because it's not involved in bonding really, right? It's not even in the plane of the carbon-hydrogen bonds. Similarly, then, we could say that these out-of-phase orbitals E and F are next. And then lastly, we would probably have the out-of-phase combination. I made a mistake when I said that was weakly anti-bonding. I'm thinking about something else. But this would be probably the highest energy combination because you now have no electron density in between the atoms. Okay. All right.
Are E and F equal?
E and F are equal in energy.
And why is it that G was higher than those?
Why is G higher than E versus F?
All just S?
Well, let's see. E and F have P character, so I guess if what happens, well, it will turn out that the relative energy level between G, E, and F is not going to be important. We're not going to really worry about that. So I don't actually have a good answer for you based on any sort of direct principles as to why G would be higher in energy than E or F. Yeah. Okay. It's hard to even compare them, right? Because for G, the node is kind of like a sphere around that carbon, whereas for these out-of-phase combinations, you've got nodes that are sort of lines. So counting, how are you going to count that? It's difficult to tell. And I would not ask you to rank those orbitals in energy. We're drawing G for an important reason, though, that we'll come back to in a little bit. All right, so you want to make a orbital energy diagram that has these orbitals on it. Energy is always on this axis as we draw these kinds of things. Our lowest energy orbital was A. And recall, and now I'm going to not draw the hydrogen atoms, even though I should, because our focus is on the orbitals. So when you look at this, please understand the hydrogens are implied. We're just not showing them. And let's see. All right, so we have all one phase here. For B and C, we have two equal in energy orbitals. And recalling what they looked like, and it doesn't really matter which one we call B and which one we call C. There was one that, oh, I'm getting emails. I don't care about my emails. Don't check my emails. There we go. Okay, excuse me for a moment. All right. Nope. Come on. There we go. So B, recall, looked like that, where we're going to have yellow lobes here, pink lobes there. There's another version of B that involves overlap above and below the plane of the page. We're just sort of recapitulating what we drew there. And then here we've got orbital D, which is just the 2pz orbital that's aligned along the z-axis. And then lastly, for reasons I'll explain in a little bit, it's not even the next orbital in energy, but we are going to draw that highest energy out of phase combination where you have the s atomic orbital on the carbon, the 1s orbitals on the hydrogens, but they're all out of phase, and we call that orbital G. Okay, when we make orbitals like this for a simple organic structure, we call these group orbitals for CH3, and this is planar CH3. Now, if you remember from our QMOT principles, we are going to first make orbitals for structures of high symmetry, like trigonal planar methyl. And then we can ask the question, what if, we know that all CH3 groups are not trigonal planar, so how does it affect the orbitals if we start to distort the geometry from planar to more pyramidal? Okay, so what if we take those CH3 groups and take each of those hydrogens and pull them over to the left of the screen, right? What would happen, and we're going to, based on how this geometric change changes the orbital overlap, we're going to make adjustments in the energy of these orbitals. So our goal here is going to be to use what your QMOT guidelines called systematic distortions in structure to go from planar CH3 to pyramidal CH3, or in valence bond theory, a CH3 that's more sp3 hybridized. Okay, so that should be all we got to do is now draw a representation for a CH3 that's sort of pyramidal. Remember, this is just a CH3 group, so I'm not saying whether we're not even thinking about whether there would be a bond there. We're just saying let's pull those hydrogens to the left. And let's see what that would do. You still have the 2s orbital on carbon. You still have the 1s atomic orbitals on hydrogen. And your text says that in terms of the overlap between carbon and hydrogen, It's just a sphere next to a sphere, so it doesn't really change much as the hydrogens move. However, your book says there begins to be a small amount of long-range overlap among the hydrogens. In other words, if I were to draw what this orbital actually looks like, if we were to make pyramidal methyl and calculate what the orbital is, it would encompass those methyl groups and, I'm sorry, it would encompass those hydrogens. And now see, we're starting to fill some of the space between hydrogens. And that's favorable, though it's a really small effect. And so in terms of energy, as we go from planar to pyramidal, this A orbital is going to go down in energy only a little bit. And the process of going through systematic distortion of orbitals to get orbitals of a new shape was pioneered by chemist A.D. Walsh, and so these are often called Walsh diagrams as you go from one symmetry to another. Yeah.
So when it says there's a small amount of overlap among the H's, there's also overlap still between the carbons and the H's, right?
Right. Yeah. So I guess we should have. Go ahead.
So the only thing that's really changing between this one and the one before is just the shape of what the orbital looks like.
That's right.
Okay. And it's just decreasing it in energy a little bit.
Yeah, because you've got a little bit of overlap between the hydrogens. And this is really useful to know that as you go from something that's planar to something that's not, at least for this lower energy orbital, it literally looks like the orbital's just leaning over a little bit with the hydrogens. You don't need to calculate that. Now with the principles, you can predict it, and it sort of makes sense. All right, let's talk about orbitals B and C. All right. So we're going to draw first what the distortion would do, and then we're going to decide what it does energy-wise. So here's my pyramidal CH3. For my first orbital B, I'm still going to have that 2p X orbital on carbon, and then I'm still going to have 1s orbitals on hydrogen. Okay, so compare those two. What do you think overlap looks like when you compare those two? Does it get better when it was trigonal planar or better when it was pyramidal? Yeah, you're right. Why would you say that?
The hydrogen, especially the top hydrogen, is a lot more aligned.
Yeah. Yeah, that top hydrogen is overlapping quite a bit with the orbital on carbon, whereas here it's not pointing. The 2py orbital is not, or x, whatever it is not pointing directly at that hydrogen. So yeah, worse overlap, and it's not hugely worse, it's slightly worse overlap. So B is going to be a little higher in energy. I can't draw straight lines over long distance, so I'm not even going to try. B is going to be a little bit higher in energy than the new B, when we distort, is going to be higher energy because of poorer overlap. It may be useful for you while you're still learning about these things and thinking about them to actually draw what you think that orbital looks like if we were to actually do the calculations. And you would see a lobe of electron density here and a lobe of electron density there. And it looks very much like a p orbital that simply encompasses the whole CH3 group. We're going to have a name for this kind of orbital. We're going to call this a pi CH3 orbital. Because just as we combine two p orbitals side by side to make a pi bond, imagine taking two pyramidal methyls side by side to make ethane, and you would have side by side overlap of those pi CH3 orbitals. Okay, let's do the same.
I have a question.
Go ahead.
So the principle 11 was better overlap equals greater stabilization.
Uh-huh.
So in the first example, we had more like long range overlap. So we have more overlap, meaning it's more stable.
Yep, so we went down in
So
energy.
we went down.
Yep.
Okay.
And here, because overlap gets poorer, we're going up
Okay.
in energy.
Oh,
And other questions? A similar thing happens to our C orbital. I'm going to draw, again, the pyramidal methyl group. And remember, our C orbital came from the 2p Y orbital coming out at us and back into the page. So we'll pick up the phase colors there with a proton going forward and a proton in the back, but I meant to do that with gray, sorry. And then in phase overlap above and below. But we've got the same issue with C that we did with B. Recall with B, you've got direct side-by-side overlap of these two lobes. And now when we go to pyramidal, it's a little bit further away. So again, slightly worse overlap. Not hugely worse, but slightly worse overlap. So the new C is also going to be higher in energy than the original C. And again, if we were to draw what this orbital actually looks like, what we would see would be a lobe of electron density above the plane and then behind the plane of the page with a lobe here and then opposite wave function here where the XZ plane is the node. And you can see that both of these orbitals have the same overall shape. So they're the same in energy. We'll call both of them pi CH3 orbitals. Huh, how about that? Those kids don't look like that anymore. Nor do they fit in the, they didn't fit then. You ever tried to get into one of those shopping carts at Macy's when you're too big? It's kind of painful. So there's slight destabilization as we move the B and C orbitals around, slight stabilization as we go from the trigonal planar CH3 to the pyramidal CH3. This pyramidal CH3 orbital we're going to call sigma CH3 because you could imagine this part of the orbital overlapping with something else to make something like a sigma bond. End on end overlap of orbitals is sigma type bonding, side by side is pi type bonding.
So is that why we're not really considering like a lone pair of electrons on there or another hydrogen because we're going to be involving this in bonding?
That's right. Yeah. So Samantha's question is great. Is this why we're not yet thinking about even how many electrons this CH3 group has? Yeah, because we're going to make bigger things out of this. It's like we're building smaller subunits that we're then going to put together to make larger molecules. Okay. Now, this one's kind of fun. Let's consider what happens to that 2pz orbital when we go from planar to pyramidal. So I'm going to draw us a pyramidal CH3. Recall that in the case of the 2pz orbital, the reason we didn't have any orbital out on these hydrogens is that they were all in the xy plane and therefore were in the node, and wave function had to be 0. But when we go pyramidal instead of planar, suddenly those hydrogens aren't in the node anymore. So now they can contribute and overlap with that part of the 2pz orbital. Oops. Sorry, what color do I want? Yellow. And what do you think that does to the energy of that 2pz orbital? It should go down, right? Why? Because we have new overlap where we didn't before, new CH overlap. And going from 0 CH overlap to quite a bit of CH overlap actually should take us down in energy by quite a large amount. And, you know, I'm not putting real numbers on this, so it doesn't matter. I guess we need to make some space.
Do we have any hydrogen overlap there?
Between the hydrogens? Yeah. Yeah, in the same way that we would here too. Good, yeah, good point. Only this time it should be even better because you actually have some of the p orbital actually pointing back into that space. All right. For reasons I'll discuss in a minute, I'm putting this orbital there. And then finally, this orbital G, if we go to the pyramidal methyl, it actually does basically nothing when we move those hydrogens out. They weren't, they were out of phase anyway, so there wasn't really a stabilizing interaction. So there's not much change here. Okay. All right. Comfortable with where we are so far? Now, there's one more thing we have to do. I want you to look at orbital D prime. What kind of bonding interaction do you think that orbital D prime could engage in? Sigma. Okay, right, Heather. Why do you say that?
It's similar to the other sigma when it sticks out towards the other carbon.
Right. This would, if you put something else here, this would stick out towards it. And in fact, it's exactly that sticking out that is the reason for the name behind this orbital. We will call it sigma out. All right. So at least in terms of the kinds of interactions it could engage in, a sigma type interaction is certainly what this orbital would do. It's what this one would do, and it's even what this one would do. Now, there was a rule I skipped over in QMOT, I think it was number 7, and that is that if you have two high energy orbitals that have the same kind of symmetry, and I'm sorry, I don't know where this rule comes from. I think it's mostly something you have to memorize to get the right answer. So when you have two orbitals of similar symmetry, that is capable of similar types of bonding interactions, those two highest ones you mix together. Oh, sorry, I'm saying it wrong. Okay. We've established that orbitals d prime and g prime have the same kind of bonding interaction. However, if you look at the carbon that would be involved in bonding, up here it's an s orbital, a 2s orbital. Here it's a 2p orbital. So to make things consistent, and again, I don't know why the math requires this, we will mix G and D together in a way that makes a hybrid, how do you spell? Hybrid shaped orbital, atomic orbital on carbon. So valence bond theory should help us out because we know exactly what happens when we mix a 2s orbital with a 2p orbital. What that's going to look like is simply a small lobe here. Oops, come on. A small lobe there, a larger lobe here. That looks exactly like you may have drawn an sp3 hybridized orbital before. In terms of what that should do to the energy here, you go from something that has a lot of p character on carbon to something that has a mixture of s and p character. S orbitals are lower in energy than p orbitals, so this one goes down even more. So I don't know where we want to put that. Maybe we want to put it here. D double prime, I guess. And this is, now that we've sort of remixed and changed that orbital in the middle, that's our sigma out orbital. It won't matter what the G prime looks like once we've mixed it together. If you wanted to, and I'm not sure, how much or lower in energy it would be. I'm not even going to put that on this diagram. I think your text shows it, and that's fine. It's high enough in energy that it won't really affect anything. You'd simply draw it like this with an out of phase interaction here. And you might expect that to be higher in energy than the G prime orbital that you started with.
Wait, how are you getting G double prime? What are you mixing?
We had to mix, remember, because G prime and D prime share the same kind of bonding interaction that they could participate in, and because they differ in the identity of the orbital on the carbon, one is S, one is P, we're going to mix them together so that they both have the same kind of orbital on carbon.
Yeah, so that's how you got D.
That's how I got D, and get G from that too. You turn the 2s orbital into a sp hybrid type orbital. Why it's pointing that direction, I got nothing.
Why did we still also call it G prime prime? Why, since we are missing since it's a mixture of D and G, why not?
Okay, that's why do we call it G prime prime, since it's a mixing of G and D? I suppose if you wanted to, you could call, I don't know. I suppose you could say this is some mixture of G and D that's lower in energy, and this is some mixture of G and D that's higher in energy.
So really, there's just going to be two different mixtures. One's going to be higher, one's going to be lower.
Yep, and that's where we're going to see this kind of sigma out orbital all the time. And you may start to wonder, why does it have that weird shape where a lobe is bigger over here? And it's because we took that p orbital and we mixed in some s character.
Okay, sorry. Initially we said that D prime was sigma out also.
Yes, it would be fine to call this sigma out. The difference is subtle. But the idea is that this orbital is distorted to have even a larger lobe on this right-hand side, which should make it even better at bonding. Okay. Yes?
So why did that happen?
Sorry, say it again?
So why did that happen that the orbital on that side is a little bit bigger?
Why does it happen? Because the orbital on this side is a little bit bigger. Well, when you mix s orbital and p orbital together, you get a hybrid orbital out. And mixing the p orbital where they're the same size on either side with a sphere decreases the size of the. It's a good question. Let me just think about it this way. Imagine combining a p orbital like this with an s orbital like this. you've got an out of phase cancellation here. You've got an in phase reinforcement here. So you do that math and you're going to have an orbital that looks like that.
So on that G double prime, the yellow side was you're trying to show is bigger than the pink side.
That's right.
Okay.
Though that issue is minor and not important. And really, I don't know. Alvaro, is that an okay answer to your?
I guess I'm still confused because I guess the way you drew it out in my head, like the canceling out part is the same thing as the in-phase part, so I see it as it would be the same.
Right. So let's do it this way. And I'm going to do something I never do. Let's suppose that wave function is negative here and positive here. That doesn't mean charge. That just means wave function sign. And let's suppose this wave function is positive. Okay. You superimpose them, mix them together. I'm going to highlight regions of positive overlap here where they're going to add together. And here you've got places where they will offset each other. Right? And so the magnitude of what you've got over here in the negative side is going to be smaller than what you've got on the positive side. Okay. And this rule number 7, whereby we mix this 2s orbital character in the G prime orbital with the p character in the D prime orbital, that really is just a rule you have to remember to get the right answer. Okay, so now we're able to ask an interesting question that's going to help you understand molecular geometry at a fundamental level. So let's consider, even though we've said this is CH3, one of the rules of QMOT says that you can change the atom in the middle and it doesn't make a big difference in terms of the orbitals. So let's ask about BH3, which comes with 6 valence electrons. And let's ask the question, which arrangement is more stable for BH3? Is it the planar arrangement or is it the pyramidal arrangement? So to do this, what you do is you fill the orbitals up with the available electrons. We've got 6 valence electrons. Okay. Which situation is better? Planar. And it's hard to tell because the real question is how much is that stabilization that you get from having slightly better long range overlap versus the destabilization you get by having poorer direct end-on-end overlap. And it turns out that the destabilization you get here is larger than the stabilization you get here. Stabilization, small. And so for BH3, if it distorts its geometry from planar, those electrons are going up in energy. So it prefers the planar geometry. Okay? Whoa! MO theory just told you exactly what valence bond theory and valence shell electron pair repulsion tells you. That's about keeping electron pairs as far apart as possible. MO theory has a different explanation, but it comes down to the same thing. That geometry is more stable. Okay? In contrast, let's consider, I guess BH3 we used blue. And I realize we're out of time, but it won't take us much time to do this. Now let's think about ammonia, NH3, 8 valence electrons. Now what do you predict? Trigonal planar, right? Whoa, wrong answer, Josh. Pyramidal, yes. Why? Because you get a huge decrease in energy when this orbital is filled if you'll go pyramidal because you introduce bonding interactions where there weren't any. Isn't that awesome?
Yeah, that's
Yeah.
Yeah.
It is.
My mind blew up when I saw that. It was crazy.
I was
So,
like, okay.
all right, there we go.
This is awesome.
And with that, we're going to do crazy